Hey everyone, and welcome back to Prefusion. I'm Manish, and today we will be starting the new conceptual question series, right? So I have done already one question, and on control system, that is basically on state space analysis, which is on controllability and observability. I hope you have watched that video. Very important. Like at least I can expect at least one question, right? At least 2 marks I can expect from that state space itself, and most hot topic is controllability and observability, right? So what is the next topic that we're doing here? We're doing here the time response chapter, right? And from time response we are mainly focusing on the damping concept basically. So yeah, like you might see, like you might say that you have seen this circuited and this is like a transient question, like why is this in the control system topic? So basically if you read the question carefully, right, you will understand. So let's read the question first. The question says the circuit in the figure contains a current source driving a load having an inductor and a resistor in series with a shunt capacitor across the load. The ammeter is assumed to have zero resistance, so it is an idle ammeter basically. So we have a shunt capacitor and a load which is a RL load basically, okay, so which has a resistor and inductor in series, and the switch is closed at t equals to 0, right? Initially when the switch is open, capacitor is discharged and ammeter reads 0 ampere. Basically it says that there are no initial conditions in the capacitor or the inductor, okay. After the switch is closed, the ammeter reading keeps fluctuating for some time. Now what does what does he mean by this sentence? So ammeter reading is fluctuating. Let's say this is my, okay, I will draw this like this. This is my pointer, right? This is my pointer and this is like the scale that I am looking at. So ammeter reading is fluctuating, it is going left right, right? You see whenever you go to the lab, right, and you measure something, measure some current and or voltage, right, you see that your ammeter doesn't directly go to that final value. What happens? It oscillates. I have also explained in my full theory class also that why does this happen, what is the reasoning behind this, right? So like all those things have been explained in my like time response lectures basically. So here I don't have enough time. So like this is happening now. If this is oscillating around some steady state point, what does this mean? This means there is some damping present, right? There is some damping present. So this is a question of basically that question of damping, and this is basically question of underdamped system. Why? Because here, right, the question tells us it keeps fluctuating for some time till it settles to final steady state value, right? Okay, as it fluctuates, then it settles to final steady state value. This is a question of underdamping, right? Now if there was no damping itself, right, it directly goes to the steady state value. There could have been two types of damping over there. It could have been either over damped or it could have been critical damped, right? So critical damp would have reached its steady state faster, and over damped will take more time to reach its steady state, right? So those are the difference between critical damp and over damp. So I'm just revising you guys what the different types of damping and what will happen in undamped. Basically there won't be any like damping, so hence it will never reach steady state, it will never settle. Here it has told us that it is settling, but for undamped case it will never settle. What will happen? It will always keep on oscillating, right? It will never settle, okay. So that was basically a bit of revision about the overdamped, underdamped, critical damped and the undamped case, right? So now what is the question asking us? The question is asking us, we have to find the maximum reading that one will observe just after the switch is closed. So we have to find the peak value, okay. We have to find the peak value. So if you remember, right, if you just remember, I will quickly recap you. So if you have studied the time response chapter, whenever we gave an unit step, right, and this is basically a unit step. Basically like at t equals 0 we're closing this switch. So before t equals 0 we don't have any input, so u of t equals 0, like u of t less than 0 is 0 and u of t greater than 0 is 1. So basically this, right, this is like a unit step input itself, right, like control system whatever is studying. So if we give a step input, what is the response we get? The response is something like this, right? It oscillates around the steady state point and it then settles, okay, then settles. Now what is the question asking us to find? The question is asking us to find this first peak, okay. The question is asking us to find the first peak, okay. The first peak will occur at TP and it is asking us to find the first peak. So what you can do, you can solve this using two methods, okay, using two methods. What is the what are the two methods? First is obviously like you have to find the zeta, omega n, omega p, all those things, right? Else you will not be able to solve this. So how to find all those things we'll see, but first like we have to find the steady state value itself, right? They haven't told us a steady state value. So this is a combination of question of both transient and the control system. So this is a very good question, and what I will recommend you is basically you solve this in the second round or the third round. So generally when you solve an exam, right, you solve in rounds. So basically in the first round you try to solve the easy question and the questions which you know. In the second round you try to solve those questions which you couldn't solve in the first round and which were difficult to you, right? And in third round you solve the remaining questions, right? So this question, right, is either in the second round or the third round depending on your confidence. Okay, so this is not a first round question because obviously this is not simple and this will take you time to solve, right? So that's why you should always try to focus on the easier questions on the first round. That's for the strategy basically. So now let's find the steady state value, right? Steady state value. Steady state value, right? So what about the steady state value? Basically if I just draw the circuit, right, at steady state what will happen? Like initially there is no current, so I'm not drawing, and like Himanshu, like if you have already learned from Himanshu, right, so he have taught you like transient very well of all these RLC circuits, right? So like you are already expert at this, but still for people like at steady state what will happen to the capacitor? It will be open circuit, right? As it is a stable circuit, capacitor will be open circuit. Okay, now what will happen to the inductor? It will be short circuit, right? I will make it short circuit, just wait a second. Okay, this is short circuit, okay, and this is open circuit, right? And this our resistor 5 kilo ohms, right? So this is 5 kilo ohms. So what will happen? Obviously here we don't have any path of current, so obviously this whole of 1 ampere, right, will always flow from here. Okay, and what is the thing that we are measuring? We are measuring the current through this load, right? So the value of current through this load is 1. So let's say our y steady state equals to 1 ampere, right? So y steady state equals to 1 ampere itself, right? And this is our y of t, okay, and this is our t. Okay, so we have to find the first v. So how to find that? So if you remember, right, so if you remember correctly, what was my equation? What was my response equation? So my y of t, okay, I can write my y of t as y of infinity into 1 minus e raised to power minus zeta omega n t divided by, okay, sorry, under root, no, this is the, okay, no, this is like this. Like if you don't remember this equation, that is fine, you don't need to remember this equation. Okay, like this is the method 1 how you solve it, and method 2 is also there. Like many people are not able to remember this equation, but I will recommend you have to remember this equation because this may come handy in some other case, right? Zeta is going to sine omega d t plus theta. Now you might ask, sir, what are these things? So I have taught this in my lectures, so yeah, we don't have enough time to solve here, right? So this is the method 1. Basically what you do, okay, method 1. So method 1 is you find the peak time. Basically what is the peak time? T peak will be simply pi upon omega d, right? T peak will be pi upon omega d. Now you just put the value of T peak here, right? T peak here, you have to find the zeta and the omega n, okay, and you will get your answer. Okay, you will get your answer. So your answer will be y of t at t equals to Tp. This is your answer. Okay, this is one way, bit of like you can do this. This is also simple, but you have to find zeta omega. So obviously you have to find zeta omega. That is important, right? Now what is the method 2? Method 2, right? So before finding the method 2, let me tell you how we will find the zeta, omega n and omega d. So for that what we need? We need the characteristics equation. Characteristics equation of what? The transfer function, right? So what is my transfer function here? So what is my input here? The input is this current source. Okay, now you might say, sir, like this current source is 1 amp, so I can assume this as a Laplace transform. Yes, you can, but what I will recommend is like you assume this as input, so you write this as ii, a unknown variable. You don't write this as a step 1 amp of current. Okay, why? I will explain. Okay, so yeah, now this is my input and what is my output? What is the response that I am checking? This is the input that I am giving, and what is the response that I am checking? I am checking the response of the ammeter current, that is the IL, right? So or y you can write. So basically IL of S upon I of S, right? So for different input currents, I'm checking the response. Okay, in this case, yeah, my current is 1 amps, that is fine, but it may also change, right? It may also change. So I have to find the transfer function between the input and output. So how to find it? So basically, if I draw the circuit again, right? If I draw the circuit in a better manner, this is my input current source. Okay. Now I will convert everything into Laplace domain, right? And this is the inductor. Okay, this is SL. This is R is same only, and this is II of S. Okay, we write this as a input function, which is function of frequency. Okay, Laplace domain. And what is the response that I am measuring? I am measuring the response here, right? This is IO of S. Let's say, or IL of S. I can write IL of S, right? Now let me check, is it recording? Yeah, everything is recording. Okay, so now what I can do, I can usually use the CDR, right, current division rule. So IL of S upon II of S equals to simple the current division rule, right? So okay, I will not write this here, this will be simply II of S into this 1 by CS. You write the opposite end, right? You write the opposite end of where you want to find the current. Like this load side, I want to find the current, so I will write the impedance of the opposite side. So yeah, 1 by CS divided by R plus SL and the summation of all the impedances, right, plus 1 by CS. Okay, now I'm not one thing to note here is I'm not putting the value of R, C and L. Why? Because if you put R, C and values right now, right, it will become too much messy and untidy, right? So whenever you want in the examination or something, you put the values of R, C and L at the end. When you get your final equation, then only you put your values of R, C and L, right? Else here, if you put your values, you might do some mistake. There are higher chances of doing mistake at this stage than at the end stage, and you can also rectify your mistake by seeing right at the end. But here, if you make some mistake at the middle step, right, then it will be difficult for you to rectify the mistake. So just write them as R, C and L. Okay, so from here I can get my transfer function. IL of S, II of S. So this basically becomes S square LC plus RC plus 1, right? And now what I will do, obviously the coefficient of my S square is always 1, so I will take LC common. Okay, 1 by LC S square plus, like this is a normal characteristic equation, you have seen this multiple times, right? R by LS plus 1 by LC. So like this is the most common characteristic equation that you will see. Okay, and this is my transfer function, which is IL of S upon II of S. Okay, so what is my characteristic equation? The characteristic equation is the denominator basically of my transfer function, right, which is like if you equate this equals to 0, that will be my characteristics equation. So S square plus R by L plus 1 by LC equals to my 0 is a characteristic equation. Now what is my standard characteristic equation through which omega and zeta and all the other things are related? So that is S square plus 2 zeta omega and S. Okay, omega n square equals 0. This is the standard characteristic equation. Now we will obviously compare with this. So if even if you remember, right, you can remember this, like my omega n will be 1 by under root LC, and what will my zeta will be simply R by 2 under root C by L, right? So I have also told in my full class how to remember all these formulas, right? So basically from here I can understand omega L will be 1 by under root LC, and what will my zeta simply equals to 1 by 2 R by 2 under root C by L, right? So zeta, like if you equate that, you will simply get r by 2 under root c by L. Okay, so this is my zeta and my omega n. So now here you put your values of r, c and L, right, or omega n. Okay, but before that I want to go to the method 2. So what is the method 2? Basically method 2 is basically the formula, right? MPO formula. Okay, MPO formula, like obviously that formula came from here itself, right? That formula, right, that formula came from here itself. Instead of just putting it here, like putting the values here, what you can do, you can directly write like this, right? You can directly write like this, that your what do you say, y of t peak, right, or maximum peak will be equals to y of infinity into 1 plus e raised to power minus pi cot theta. Okay, so this is what you can write. Okay, so like how did this came? Obviously if you put the values here, right, if you put the values here, this sine omega dt and this 1 upon zeta square will get like cancelled, and like you will get something like this, pi upon cot theta, right? Okay, so yeah, that is basically it. So basically if you put the value here, like you will get this equation only. So if you remember this, right, you don't need to you use that equation, you can directly skip to this part, and you don't need to find the t peak, right? You don't need to find the t peak, just you need to find a y of infinity, which you have already found out, and you need to find the cot theta. Now what is cot theta basically? So cot theta, right, like what is theta? Theta is basically like, or cos theta is, we know, equals to zeta, right? So like if you don't understand anything from here, then like you don't need to understand basically. So this is the end stage, you don't need to understand, like just remember that cos theta is zeta. Okay, how this cos theta zeta came, all this I have explained in the full lecture, so I will not explain further here, right? Cos theta is equal to zeta and theta equals to cos inverse zeta, right? So yeah, zeta we will find out from here, right, and we'll put here and simply find the answer. We don't even need to find anything else. We don't need to write any equations, right? So that's why I don't recommend using this formula. Okay, like this formula, like this formula, right, this came as a result of this putting t peak here, right? Putting t peak here, that came here, right? So basically that came from this only. Okay, that's why I will recommend directly remember this formula. This will be very handy. And what is your MPO? What is your Mach peak overshoot? This part is the my max peak peak overshoot, right? Okay, I hope something like you are recalling everything, right? You are recalling everything. So this is my theta. So like what is my zeta this time? So yeah, zeta is basically r by 2 under root c by L. So what is r? R is 5 kilo ohms basically. R is 5 kilo ohms. What is my c? C is 100 pico and L is 10 millihenry, right? So R is 5 kilo, C is 100 pico and L is 10 millihenry. This is picofarad and this is kilo ohms. Okay, so R is 5 by 2 into 10 cube. Okay, and C is 100 to 10 to the power minus 12. So whenever you're putting these values, right, put it very cleanly and very carefully, right, so that you don't make a calculation mistake. So it happened with me multiple times that I made few calculation mistakes, right, during my time. So yeah, just put them write them a bit slowly and like calculate in a clean manner. So L is 10 into 10 to the power minus 3. Okay, so this is basically my L. So this is 2.5 into 10 cube, right, and this is under root 10 into 10 to the power minus 9. Okay, so 10 to the power minus 4 we have, so this becomes 0.25. so my zeta is 0.25. now what will my theta? Theta will be simply cos inverse 0.25. now I have already written it down, like cos inverse. What is cos inverse 0.25? it is simply something around 75.2 degrees, right? 75.2 degrees. This is what my theta is. Okay, this is what my theta is. Now what do you do? Simply you have to find the peak value, right? Simply you have to find the peak value. So for finding the peak value, what is y of infinity? Y of infinity is basically 1, right? Y of infinity, yeah, y steady state value is 1. That is basically my y of infinity here. Okay, y of infinity is 1. Or like you could have done here, right? Use the final value theorem here. That would have also sufficed. Okay, or you can find it from your steady state, like transient response also. That is more easier. Here what you do, you now put the value of, like if you want to use the final value theorem, what you do, you put ii equals to 1 by s. Okay, because it is like a unit step input, and the amplitude of it is 1. The step is 1, right? So you put 1 by s here, like 1 by s goes here, and then you multiply s with 1 by s, and then you put s equals to 0. What will see? You will see 1. So I will show you. Okay, let me copy this one. Okay, I'll show you what do I mean by that. So you don't even need to put the values, right, of L and C. So if you want to find the steady state load current steady state, right, what do? You do S using the final value theorem, right? Limit as s tends to 0, s I of s. Okay, so what is this? This is basically s into ii, right? What is ii? Ii is like a step function which is 1 by s. So this ii, right, goes here, right? This ii goes here, okay, and this ii equals to 1 by s. Okay, so yeah, ii equals to 1 by s, and limit we have s tending to 0, right? And in the numerator I have 1 by LC, and denominator I have s square plus r by ls plus 1 by l. Okay, so this cancels out. This is 1 by LC. Okay, now if I put s equals to 0, this becomes 0, this becomes 0. We are left with 1 by LC by 1 by LC. So 1 by LC by 1 by LC is 1. So yeah, that is, like, from here also you can understand the steady state value will be 1 itself. Okay, both ways you can go, whichever you are suitable with. Okay, so yeah, now what is my calculation basically? So now this is 1 into 1 plus e raised to power minus pi cot theta. Cot theta is basically whatever the value is, like I have not calculated that. The final value which I will get, right, final value which I will get is this 1.44 amps. So this will be the peak value that I will get. After that it won't go more than this. Why? Because this is the type of response that I will get, right? Because this is the first peak. Then what will happen? The damping will come into effect, hence more friction will be there, hence obviously I can't go more than this. Okay, that is the case. Now one thing I wanted to ask is, I wanted to find out is, can you find the minimum value? Here, right, it has told us the maximum ammeter reading. Can you tell me the, after reaching the maximum ammeter reading, okay, after reaching the maximum ammeter reading, once the ammeter has reached this point, right, after this, can you tell me the minimum ammeter reading? What is the minimum ammeter reading that this current can go? Okay, what is the minimum ammeter reading after reaching my first peak? Okay, so you can understand, there is some concept of undershoot, overshoot, all those things. If you think about that, you will be able to answer it. So yeah, that's it for this question, and if you want more questions like this, then don't forget to hit the like button, and I will see you in the next video.